Hello. So in this video, we will be starting building our abstract syntax tree. We'll start parsing the expressions. Till now, we have been able to break down the source code into digestible tokens, and now we need to do something with them. So if you were to read the instructions for this stage, they tell you to read the chapter 5 of the book, Crafting Interpreters, and they use the code from this chapter, and I recommend you read that too, but I'll do my best to try to explain everything to you, but definitely the explanation in the book is going to be better than mine. So let's just read what they tell us to. Before starting the stage, make sure you have read the representing code chapter 5 of the book. The code covered in that chapter, AST printer, will be required to generate the output. So I will write the AST printer as well. You don't need to read the book, you can just follow along with my videos, but I do recommend reading the book. The code for this stage is implemented in section 6.2, basically chapter 6 section 2, and so they just tell you to read the chapter 5 and bring that code into your own implementation as well. I'll write the code for that. So in this video we won't be passing any of these stages, we'll be writing the AST printer class. Okay, and they're going to be testing. So we are not doing this right now, we are going to be building the printer right now. So what the printer does, let me show you. Till now all we have is a lexer, and what it does is it breaks down the source code into tokens that we know, into the lexicon of the language. And we do not have it formalized. Like we know, like a plus is a lexicon in the logs language, 1 and 2 are numbers, right? But we do not have any formal rules. Lexicon doesn't require rules. We know the alphabet of the language and we can identify and tokenize them. But going forward, we need some kind of formal representation of the grammar, of the rules of the language. All right. And we will build out the grammar for the language and the grammar of the language, the rules. All right. And we define the rules in something that is called the context-free grammar. Let me show you what that means with an example. For instance, let's take arithmetic expressions, right? And as you can see, we have this expression 1 plus 2, and it can be expressed in the form of a tree. Right, the operator is on the root node, and on the left we have a tree leaf node 1, and on the right we have another leaf node 2. So we can evaluate this expression by doing an in order traversal, right? Left, root, right, and that gives me the evaluation of the tree of the expression as it should be. All right. So if we were to formalize this grammar, this arithmetic expression, it could look some. Let me write that in the README. All right. So instead of writing that in the README, let me create another file called the CF. Let me call it cfg.md. cfg.md. All right. So if we were to formalize it, it could look something like number operator and then a number. That's an arithmetic expression. All right. So there is going to be a number, then it's going to be an operator, then another number. Like the operator can be a plus, a minus, an asterisk, a divide, or whatever. All right. But that's only a binary operator. In the logs language, we support unary operators as well, right? We can have a minus one, minus one. Wait a minute. Minus, what the hell? Minus one. What's going on? Anyways, we can have a minus one, right? We can have a minus one, or we can have a negation of a true. So negation and minus are unary operators that we support in this language. All right, and for that, our arithmetic operation should expression should look something like operator then a number, or an operator then a boolean. All right, something like that. That's how our arithmetic expressions should look like. It's either that or this. Like, let me use the pipe symbol for or. So something like this. This I can call this an arithmetic expression in the logs language. All right. So this format that I'm using, this pipe symbol for an or, this just the syntax of the context-free grammar. That's how you define a context-free grammar. All right. So we can call this rule binary and this a unary, and we can break those down. All right. So we can separate those out into different rules. So binary can be equal to number operator and then a number, and a unary can be an operator, then a number, or an operator and then a boolean, right? But like I showed you, it's not necessary that our operator is applied to a number. Uh, like it can be a boolean, but it can also be another expression. Let me show that to you as well. So we can apply these operators to other expressions as well, right? So this plus in the middle forms this root node, and then this expression in the brackets become this left side node, and this one becomes the right side node. So therefore, our binary and unary operators can be applied to other expressions as well. It can be applied to a binary, and it can be applied to another unary. All right. So we need some form of a recursion. We need some recursive data structure to be able to express it, right? Because a tree, for instance, the left node of the root in a tree can be a subtree as well. So we need some rule that defines recursion. We do not have that right now, right? So let's create an expression, a base expression that will be recursive in nature. So expression, and then it is an expression operator expression, right? This is a recursive rule. All right, this will give me a tree node that will be recursive, but this is a infinitely recursive, right? We do not have it. We do not have the recursion ending anywhere. Expression goes into expression, and then expression goes into expression again and again and again. All right, and we also need a way to be able to distinguish between unary and binary operators, binary expressions. So instead of defining expression like this, let's just define it like unary or a binary, right? Let's define it like this, and our expression also requires a base condition. So when does recursion end? When we have a number literal at the leaf node, right? When we have a 1 or a 2 at the leaf node, that's where the recursion should end. So expression can go into a literal as well, all right? That's where the recursion would end. And an expression can be a binary or a unary. So let's formally define the unary and binary expressions as well. So a unary could be an operator and then another expression, right? And a binary can be an expression, then an operator, and then an expression again. So that will be a binary. And this format that I'm using to write the rules down for a programming language, that is logs, is just called the context-free grammar. It's just this syntax. Context-free grammar is just the syntax we are using to write down the rules of the language. All right. So we have this literal, but we do not have it defined anywhere. What can be the possible values of a literal? In the logs language, a literal can be a number, or it can be a string, or it can be boolean, but there are only two possible values for boolean, that is true or false. Just define it. And the other value it can be nil basically. So that will be the literal in our language. And this grammar can be used to create a syntax tree. like the one we created for the arithmetic expression, we can use these rules to create a tree for everything in a language. But let's only focus on basic operations right now. So by the end of it, we can get something like a calculator. So these are all the rules put together, but we are still missing something. What are the operators? I just wrote operators, but we haven't defined the operators. What can the operators be in our language? So we should define all the tokens that are allowed to be operators in the rules of the language. Like in English, we have punctuations, right? So we should define what all operators are allowed. All right. So operator can be, let me just copy that and paste it, right? So those are all the operators that are allowed. We have a double equal to, we have a not equal to, we have a less than, we have a less than equal to, we have a greater than, we have a greater than equal to, we have a plus, minus, asterisk, and divide. Right? Those are all the operators. All right. But in the base, like in basic mathematics, arithmetics, we have the BODMAS rule. So we need something like brackets for precedence control. All right. So we should add a rule in our language that will give me that brackets as well. So let me add that. After the expression, let's create a base expression as well. That's called a grouping. And this is going to be an expression surrounded in brackets. All right. That's it. That's all it's going to be. So that is another rule in our language. These are all the rules that allow us to do basic maths. We need to take care of precedence as well when we evaluate that abstract syntax tree we will be building. But we do not have to take care of that right now. We can take care of that when we get to the next stage, evaluating the expressions. But right now we are just building the expressions. So what do we have now? As of now, our interpreter just has a list of tokens. Now I need to put those list of tokens into something in a normal language would be sentences. Like in English, we would uh, use those alphabets to make words and then use those words to make sentences. So right now we are making words, all right? And after that we'll make statements, and those statements kind of like equivalent to sentences, all right? So right now a 1 plus 2 is just an expression. It's not a statement. It's an arithmetic expression. But if I were to, why is it not working? Why is it not working? So if I were to just write true, that's a Boolean expression, not a statement. All right. A statement would be something like assigning var equal to true. This would be a statement. This is like a sentence in our English language. This is a sentence in the Lox language. But a true is just a Boolean expression. What we're doing right now is we're using the lexicon, the alphabet of the language, to build up the words. A programming language which is very specific allows us to represent the entire language in form of trees. So we'll be building these trees out of these languages, out of this context-free grammar. All right. So how about how to go about building the tree? So if you do lead code questions on trees, you typically get a single node class that serves as the root as well as the leaves. We can do that and assign a type to each node, like token types. Like we've been assigning token types, we can assign node types, and the node types can be expressions, grouping, unary, binary, literal, operators, right? And that's how we can define different types of nodes in our trees. All right. But why would we want to do that? Because when it comes to evaluating the tree, we need that token type uh, to identify that different nodes should be evaluated differently. A unary is evaluated differently from the binary node. All right. So when we get to evaluating these expressions, that tree, that type will be very helpful. All right. But what if we inbuilt the type system into the tree? What I mean is, instead of defining a type enum, what we can do is define different classes for different types of nodes. So a binary can be a different class, a unary can be a different class, a literal can be a different class, and an operator can be something else, an expression can be a different class, and then we can use the instance of operator in Java, instance of operator in Java to conditionally do different types of logics. Right, so we'll create different types of node classes, and then we can use this instance of operator to know if we are at a leaf node or not. So let's turn these rules into classes whose objects are like those objects you get in typical lead code questions. All right, and that would allow this instance of would allow us to do a discriminated union. What that basically means is the base class for a unary and a binary is same. We'll extend it from an expression class, but since a unary is an instance of unary and a binary is an instance of binary, based on this condition, based on this if check, we will perform different logics. We'll dispatch different implementations of evaluation. So that is what's discriminated union. Anyways, let's just start building our tree out of these rules. All right, so let's see what packages do we have. We have a lexicon. Doesn't make sense to put this in a lexicon. We already have a lexicon. We have the keywords, we have the tokens. So let me create a new package and let me call that syntax, as this is the syntax of the language. And in the syntax, right now we are building an abstract syntax tree. So let's call the package an AST. And in that AST, we are right now building expressions. All right, so let me create another package called expression. And yeah, so let's create the base expression class right now. All right, so this expression class is going to be an empty class, and every other expression is going to extend from this class. So expression, and let's make this abstract. It doesn't have any implementation. Other classes are going to extend from it. All right, so let's see our rules. What do we have right now? We get expression. After that, we have a grouping rule. So let's create a grouping. In the grouping, it's going to extends from expression. All right, and what does a grouping look like? A grouping is just brackets surrounding another expression. So it has an expression in itself. So let's do that. Public final expression, and then let's just call it expression, and let's create a constructor. Where is the right? So that will be the grouping class for me. Let's see what the rules say. Then we have a unary. All right, then we have a unary after. So let's create a unary class. Unary. What does a unary look like? A unary has an operator and it has another expression. So let's create those fields. A public final token. Let's call this operator. And public final, then it has an expression, right? Oh, by the way, uh, not all operators are allowed to be operators in a unary expression. Only some are. So let's change our rule to reflect that. Uh, Only a minus and a negation are allowed to be expressions. So we need to take care of that when building our abstract syntax tree. We will only build a unary if the preceding operator is a minus or a negation. And if we had another expression before it, it would not be a unary at all, it would be a binary. All right. So only these two are allowed to be operators in a unary expression. So let me make it pretty. Okay, so our unary has an operator and it has an expression. All right, and like I told you, only a negation and a minus is allowed to be an operator. So how about if operator dot what do we have in a token? We have a token type, right? So if operator dot token, then we have a token type, and the token type is minus. And so in a unary, if operator dot, let's just call this op dot, is this private? Yeah, let's make it public. Operator is not equal to token type dot minus, or operator dot type not equal to token type dot bank. In that case, we won't create, let me throw a runtime error, throw runtime exception. uh, Invalid arguments for unary expression, right? Java.lang throw, oh shit, new. So if this is the case, sorry, it should be and. If that is the case, he won't be allowing the creation of a unary operator, right? A unary operator is only allowed to be constructed if it is a minus or a bang. And if that is not the case, we'll throw a runtime exception. So that brings this rule into our Java code. So after that, in our context free grammar, we have a binary. So let's call binary. And in the binary, we have an expression, then an operator, then another expression. So public, uh, public, public final token. Then we have an operator, right? And then we have two public final expression. Then we have a left expression and a right expression. Just for consistency, just to be consistent with the book, let's call this expression right, because in the book they call it right, so I want to be somewhat compatible with the book, right? Okay, what do we do? Control Z, right, and right. Okay, this is fine. Then we have a binary. What do we have after that in our context free grammar? After the binary, we have a literal. So let's create a literal class as well. Uh, Literal. and a literal can be a string or a number or a boolean or nil. So, and a nil is represented by null in Java. So the common type for all these would be an object. So let's create public final object and then call it value and constructor. What do we have? Do we have anything else in our literal? So the operator is being handled by the token class. So that's what we will inject here, and we'll just make sure that these like in the unary, I am checking if they are minus or a bank. So similarly, when creating a binary, we will check if they are valid operators or not. So these are all the classes that will serve as the node of our trees. So the base node is going to be an expression class, and then we are going to have a binary, we have going to have a unary, a grouping, and a literal. All right. We will so the lexer, it creates a list of token for us, right? It creates a list of tokens for us. So we're going to loop through those list of tokens and check our rules. So if the first token is a bracket, then we and the next thing is an expression, and then the next thing is a bracket, we know we are at a grouping. So we'll create an object of grouping, and that will be a node in our abstraction text tree. Similarly, if the first token is a number, the second token is a plus operator, and then the third token is another number, then we have an arithmetic expression, and then we can create a binary node out of that list of tokens. That's what we are going to be doing. These are the base classes that will serve as the nodes of our trees. So after this, we can go ahead with building up the tree, but that's it for this video. All right. I think let me know if you want me to explain this concept better, but I do recommend reading the book, this chapter 5. Oh, really, really sorry, guys. I missed something. All these classes needs to be extending the expression class. So just add that. It extends expression. Similarly, a literal should extend expression, and a unary should extend expression as well. We also need to add this here because our expression can be a grouping expression as well.